Right. Good morning. How are you today? Okay, good. Right. Today we will have a new topic, which is metallic bond. So we start with this. We already learned there are three chemical bonding, right? The first one is ionic bond. Second one is covalent bond. And today we are going to learn what is metallic bond. Right. So the story starts with the electrical conductivity. Okay, this is the numbers of the electrical conductivity, and this is a unit. We use Siemens to represent this number. Okay, and actually Siemens is the reciprocal of ohms. Okay, so ohms is resistivity, right? Hope you still remember resistivity. Let me make it louder. Right. Okay, so if we have higher number of the Siemens, the electrical conductivity will be high. So I'm sure you understand this. So when we talk about ionic bonding or ionic compound, this is aluminum oxide, which is ionic compound, right? So it's kind of bonding. And the diamond is covalent bond, right? Diamond is covalent bond, and this is an insulator. So as you know, that number is 10 to minus 11. So the conductivity is very, very low. An ionic bond and covalent bond, because the electron was bound tightly between atoms. Okay, so you cannot move electron. That's why the electrical conductivity is low. So, and then we understand ionic bond. We understand covalent bond. This is also, silicon is also covalent bond, right? But the conductivity is a little bit higher. Why? Compared to diamond. Why silicon, the conductivity is a little bit higher. However, this is also covalent bond, compound. Okay, so the number of these Siemens is not high enough to be regarded as the conductor. Excuse me, conductor. Okay, so this part is what we call conductor. Graphite is covalent bond, and we understand this is because graphite is sp2 hybridization, right? So this, you have a p orbital, which is delocalized electrons. So electron in the p orbital and can deliver deliver the electrons, or can move the electrons easily. So that's why we have a good electrical conductivity for the graphite. How about aluminum? What's the bonding of the aluminum? At that moment, they don't know. They don't know how to address this bonding. Okay, how about copper, which is of silver? They are very good electrical conductors, but it does not belong to the covalent bond. It does not belong to ionic bond. Okay, and as you can see, the conductor has a very wide range of the density from 0.5 to 22.5, which is, you can find some very light elements, aluminum, which is very light. The density is low. But there are some elements which has a very high densities, very high dense densities. Okay, then why is so huge difference? However, the conductivity is always about 10 to 7 Siemens. So this is what we call metallic bonding. Right. So magnetic bonding is that the start from the free electron gas model first. We talk about gas first because when we talk about gas, that means between atoms there's no too much interactions between atoms because the distance between atoms are very large. That's why we call gas, right? And liquid will be closer, and the solid will be much closer. Okay. So in the beginning of 20th century, there's a German scientist proved. He think that the metal solid it has a atomic core, and then atomic core inside is is positive nuclei, and all the inner shell inside here. Inner shell electrons inside this positive nuclei. And the valence electron is delocalized. So this outside, these electrons are delocalized. Okay? So it looks like this is not quite bound. This electron is not quite bound by this nuclei. So it looks like gas-like. But it doesn't explain the metallic bonding conductivity and not discriminating ionic and covalent bond. So if you have this in the beginning of 20th century, this is kind of assume what the metal looks like, but there is no really scientific way to explain, and that's why they found out sooner or later they have a quantum theory of solids. You know, when we talk about Schrödinger equation talking about a gas phase, the atoms in the gas phase, and there's no theory talk about this quantum quantum mechanics in solid. However, in the 1928, Bosch, his PhD thesis said that the wave mechanics applied to the condensed solids. That means that all the atoms will get very close. So he assumed that the wavelength of the electron plus the atoms in the solid set of the regular patterns like crystal. So, and the periodic potentials act on the valence electrons. Okay, so there's a kind of boundary condition. So he tried to use Schrödinger equation to solve these problems in the solid. So he get a set of solutions. As you remember, this Schrödinger equation is an eigenfunction. So you got eigenvalue. Okay. So that's why you got a set of the wavelengths of the electrons. Okay, and then it can be moved quickly through the crystal. Right, and when we talk about this quantum theory of the solid, we realize this electron has a free energy, and then this free energy can be regarded as electronic conductivity. That's why this is metal bonding start from the electrical conductivity. And then after that, we have the band theory of a solid. This is proposed by Hitler and London in 1927. So when you, I hope you still remember when we talk about covalent bond, we talk about linear combination of atomic orbitals into molecular orbitals. We use LC-AOMO to realize the shapes of the molecules, right? However, LC-AOMO is applied to the 2 atoms or 3 atoms, even 4 atoms together. But now, the band theory of the solid want to apply 1 moles of the atoms, which is 6 times 10 to 23 atoms together, which is a large assembles. Okay, not only 2 or 3, 4. You want to put thousands and thousands of atoms together. and you want to apply shading equation together with the LCAOM. So again, let's start from the very easy or very simple case for the energy level diagram of s orbitals. So remember that when we have one atom energy level, if E energy equal to 0, that means free energy, right? Electrons. So assume we have two atoms, and this is the electron energy level, energy states, right? So assume this is copper, and copper has a 4s1. So in the 4s1 orbital, copper has a 1 electron. Okay, so if you have two coppers atom together, now become copper molecular, right? So you will do something like this. So the formation of a Cu2 is 3d10 4s1, right? So this is 8. You have two atoms of the copper, so you will do like this. So you have 2 electrons here, right? Okay, and remember this is what we call bonding molecular orbital, right? And this is anti-bonding molecular orbital. So as you can see, copper molecular is more stable than copper atom because the energy state is low, right? This is more stable. Copper molecular is more stable than copper atom. But you never heard about copper molecular, right? Have you heard about copper molecular? No, you heard about a solid, right? Solid copper. So that's why we will realize that copper solid is more stable than copper moleculars. So let's put another atoms of the copper into this copper molecular. Now it becomes 3, right? According to conservation of the energy state and and alpha principle, we will have 3 energy state here, right? Because there are 3 atoms, and then this has 3 atoms. So, and then if you want to put these numbers of the atoms together, that means this is the Avogadro number, right? 1 mole. So what can you do? How can you draw the energy state? Okay. So the 1 mole of the copper, the value of 1 mole is about 7.11 cubic meter. What does that mean? The 7.11 cubic meter you can regard as a 2 centimeter, and 2 centimeter cube. And if you have a copper which is 2 centimeter times 2 centimeter times 2 centimeter cube, that will be about 1 mole of the copper. Okay, 1 mole of copper. This is huge, so huge. And you started to draw the energy level diagram. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, if I want you to draw this energy level here, you have to draw how many times? 10 to 23 times. Okay? So this is very, very close. This energy level is very, very close. And it's very difficult to see, or very difficult to distinguish. For example, the rise of this energy level is about 1 electron volt. So when you have 1 electron volt and with this very dense energy level state, that means that each energy state is very, very close. So if you take out the gap of the 2 energy states, this energy level will be 1 out of 10 to 23 electron volt, which is very, very small. Okay, very, very small. The energy difference is vanishingly small. Okay, so when you have 1 electron want to jump from here to here, what you need is this energy. And as you know, if you give the light, the energy of the ray light, what's the energy of the ray light? 1.8 electron volt, right? 1.8 electron volt. So this is, if you have red light, you give the red light energy to this material, to this copper, and electron will jump from here to here very easily, even from here to here, because this is only 1 electron volt, right? And this is what we say band. So this is what band theory we call band. So what is band? The definition of band. Band is a set of very closely spaced orbitals. This is what we call band. And then the energy are all distinct quantum states, but almost continuous. So this is almost continuous, but it's quantized. The energy state is quantized, but very, very close. You can regard this as a continuous process, continuous energy state, because this energy is very, very small. Right, so when we talk about copper, let's think of sodium. Sodium has 3s1, right? Sodium has 3s1. So if you write down something like this, you have 1 sodium atom, 2 sodium atoms become a sodium molecule, and then 3, 4, 5, the energy level, if you go up to 30, that will be like this. But if you go to 1 more, that means 10 to what? 23 atoms. Okay? So you have 3s1, so you start to feel electrons in this energy state, energy level. So sodium 1, you have 1 electron, right? This is called atomic orbital. You have 3s1, you have 1 electron. And you have 2, you have 2 sodium, you have 2 electrons. This is called molecular orbital. And then bonding molecular orbital, anti-bonding molecular orbital, right? And you have 1, 2. How about 3? 3 sodiums, 1, 2, 3, right? How about 4? 1, 2, 3, 4, and 5, blah, 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 blah. Right, so when you have 30 energy states, this electron will half filled in this band, right? In this band. So if you have 1 more of this sodium, you will have electron will fill half of these bands, right? So this field of the electrons, this is empty. And this is bonding molecular orbital. This is anti-bonding molecular orbital. Okay? Right. So bonding, anti-bonding. And you know how to draw the molecular orbital, the shape of a molecular orbital, right? Right. So this is called bandwidth, and this is called band. So when we think of the conductivity of the copper, we know that this is half, the band is half filled with the electrons. So copper is 10, 3, D10, 10 and 4s1. So S band is half filled with the electron. So if we have a band here and copper S band, then it's half filled with the electrons. So these are all electrons here. There's no electron. Okay? And imagine if we have 1 electron want to jump from here to here, become free electron. How much energy required to jump from here to here? Very little, right? Very little. So filled and empty electrons. So only a very small amount of energy is required to excite an electron from the field level to an empty one. So only very little energy required, where it's free to migrate rapidly throughout the crystals in response to the applied electrical field. So if you have 1 electron jump from bonding molecular orbital to become anti-bonding molecular orbital, and this electron will be free. And what are you waiting? If you apply a voltage here to here, this electron is free. This electron will run from negative to the positive, right? From negative to positive. So the electron will run through this coil. So this is what the definition of a conductivity. Okay, so you have one electron here, you just give a very little energy, and electron will jump to the empty level. And you have a pair of the electron and the electron hole. Okay, you will have a pair of electron hole. So this is free electron. So again, once you apply, so this free electron will stay here. It doesn't move because you don't give the driving force to this electron. However, if you apply voltage, or if you apply electrical field in the both ends, for example, positive, negative, this electron will be forced from the negative side to the positive side. And this is what we call conductivity, electrical conductivity. Okay? And because only a little bit energy required to make this become free electron. So this is what copper is a very good conductor, right? A good conductivity, become a very good conductor. Right. So another term I want to let you know is called Fermi level. The Fermi, when we talk about the energy, this is a free electron and jump to here. You just require very, very low energy from the outside. However, if temperature reaches to 0, what does that mean? There is no energy at all in this environment. So electron will stay here. However, if you increase the temperature, just a little bit energy. If you increase the temperature to 1K, that means you have 1K energy, right? And this electron in this level might be jump to the unoccupied level. So at the temperature K equal to 0 Kelvin, only the lowest half n orbitals are occupied, and the highest occupied molecules orbital, sometimes we call hormone, is called Fermi level. This is called Fermi level. This is the Fermi level is that what the level which occupy all the electrons when the temperature is 0. Okay, so if the temperature increase, if temperature is more than 0 Kelvin, the electron can be excited by thermal motion of the atoms. Temperature is a representation of the thermal energy. So electron will move. So the population of orbitals, the P is the population of this orbital, is given by the Fermi-Dirac distribution functions. This is a Fermi-Dirac distribution function. Okay, ladies, I don't need you to remember these terms, but what you need to know is this P is the population. Okay, E is an energy, U is what? U is Fermi level. Okay, Fermi level energy. The K is what? Boltzmann constant. T is the temperature. Okay, plus 1. Okay, so by this, the Fermi level can be considered to be the hypothetical energy level, and which is about 50%. You will have possibility to find the electrons. So if the temperature increase, T3 is represent temperature. T3 larger than T2, larger than T1. The profile, this is Fermi level, and the profile can be represented like this. Okay, so this is just for your information. Right, this is for your information. If you just remove this, okay, if this E minus Fermi level is larger than 3K temperature, okay, just for your information. So the conductivity is, if you want to use the band gap, the band energy or the band to represent conductivity is like this. This is metal wire. You have half filled electrons here, and once you apply electrical field to metal wires, this energy, this electron will move from the bonding molecular orbital to the anti-bonding molecular orbital, and move. So this is conductivity. Right. So once we explain the electrical conductivity for the for the s orbital with only one electrons, and now let's take a look of the s orbital with two electrons. Okay, two electrons, sodium, potassium, copper. This is S1 is sodium, potassium, copper is S1. Only one electron, so you can have half field. But if you have two electrons, that means you will fill all the s orbitals. Then what happened? Okay, you have S1, this partially filled band. Okay, so electron can move from here. However, if you have two, like barium, magnesium, you have two electrons, and you will fill all the orbitals, right? Electrons from bonding molecular orbital to anti-bonding molecular orbitals. So the interesting thing is, if we have a solid and you have a lot of atoms put together, then s orbital and p orbital will be overlapped. It looks like this. So s orbital and p orbital will be overlapped, and this is called overlapping band. So the electron here will jump to p orbital, and this delivers the conductivity. Okay, so the p orbital bandwidth is huge, so it's overlap bands. So this is only applied to the solid, not gas. Okay, the gas phase, there's no overlap of the p orbital with the s orbital. But for the solid phase, because the atoms are very, very close, so the orbital will be overlapped. So overlap of the energies, right, continues to move the electrons upper level if the potential is applied. Okay, this energy, if you give the energy to these materials, the electron from the anti-molecular orbital will move to the p band. So this is what we call electricity. Okay, so this is the representation to tell you that this is 2s level, this is 2p level for one single electron. So for one single atoms. But if you put a lot of atoms together, this is the shapes to tell you that if you have more atoms together, this will be 2s orbital, this will be 2p orbital, and 2s orbital here, 2p orbital here, and this is overlapped, right? It's overlapped. Okay. Right. Then you might. So this is the cold band and the valence band. So what we just talked in this case is the valence band, not cold band. Okay. We only talk about valence band. So valence band will be overlapped, not cold band. Okay. So there are some there are some explanation for you here. Metallic bonding is that you have iron core, and you have non-valence electrons and nucleus. Okay. And metallic bond is found in metal and their alloys. So magnetic materials have 1, 2, or almost 3 valence electrons. So valence electrons are not bound to any particular atoms, so it's free to drift throughout the entire metal. So these electrons are very free. Sometimes we call cloud, sometimes we call sea, electron sea or electron cloud. Right. So the bonding energies, so free electrons act as a glue. You know the glue is very sticky. So that's why metal is ductile. You can pull the metals, or you can shape the metals, okay, to make it long or make it short, make it huge. So bending energy is sometimes weak, sometimes strong. It's ranged from the very large, so mercury is a liquid, right? The bonding energy is very low, which is 0.7 electron volt. So mercury is a material bond. And the tungsten is very strong. So the bonding energy is 8.8 electron volt. As you can see, 0.7, 8.8, these are huge difference. So if you have a very high bonding energy, the melting point will be very high. If you have very low energy, bonding energy, the melting point will be very low, right? So mechanical bond is found in the periodic table for the group 1A and 2A and the elemental metals. So the property of the metal, as you can see, the high electrical conductivity. Why? Because the electron can jump from bonding molecular orbital to anti-bonding molecular orbital with a very tiny energy, right? So this has a very high electrical conductivity. And not only this, but this metal also has a very high capacity or thermal capacity. Why? As you can see, this electron can absorb energy very easily, right? This can grab energy very easily. So electron in the valence band can absorb thermal energy by being excited to the lower lying empty energy level. So this electron here can absorb any type of energy, and then it jump to become a free electrons. That's why when you touch this kind of metal, you feel cold. Why? Because the metal at this room temperature absorb the energy from your finger very quick. Because your temperature is 37, right? But the room temperature might be 20, and 37, 20. So this metal can absorb your energy from your finger very quick, and that's why you feel cold. The other property of the metal is the higher reflectivity. You know, this one, in the old time you don't have mirror. This is metal copper. Okay, and the electron or thermal energy electron, the light hit this and bounce back to you, and that's why you can see yourself with this mirror, right? And why? Because metal can absorb this energy and then make it goes up, and because this is not stable, if you don't apply electricity, if you don't apply the potential into this metal, this electron will drop, and this is what we call cascade. And if you cascade, you will deliver the same energy as the energy go into this metal, and this photon will reflect back to you, so you can see yourself. That's why this is what we call high reflectivity. Okay, another one is ductility. Ductility is, metal looks like glue because you have free electrons, and because of free electron you can extend the metal, or you can change the shape of the metal, right? Okay, and the property of metal is that the good conductor of the both electricity and heat. You know that the most of metal and alloys fall in a ductile manner. So you know this. So another way to talk about electrical conductivity in metal is that this is what we call Newton candle. Okay, so one electron here and start to move. It doesn't move from here to here. It push the electron from here to go to this place. So that's why we call Newton candle. Okay, just for your information. So this is a summary of the metallic bonds. Right. So next topic is that the conductor and semiconductor and insulator. Just now we learned what is the conductor, which is metallic bonding, right? And insulator, it can be covalent bond, it can be ionic bond. So what happened? What's the semiconductor? Okay, let's start from the story of the diamond. Diamond is an insulator, right? This is 14 group in the periodical table, or sometimes we call 4A group. Okay, this carbon, silicon, germanium, tin, and lead. So the diamond, you know that because the diamond is sp3 hybridization. So you have 2s2, 2p2, right? And if you have one atoms in a gas phase, this is energy level, right? Energy state of 2s and 2p. And because this carbon need to have 4 carbons surrounding bondings to become a spectral distribution of the carbon. This is in the center, right? So what you need to do is 1, 2, 3, 4, and you hybridize the orbitals. That become sp3, right? sp3. So the sp3 is you have 1 electrons in each energy state, and this is a single diamond in gas. However, if we have one more of the diamond of these structures, we call this diamond, right? So what happened to this one? So you have 1 to 1 and you have 2, right? So in the end, you will find something like this. The interesting is that you have a gap between the bands. Okay, it's not longer easy from this electron jump from bonding molecular orbital to the anti-bonding molecular orbital, because you have one more and because the band stack like this way. So this is what we call band gap. So diamond is not, the electron in the diamond is not easy to jump from the bonding molecular orbital to the anti-bonding molecular, because you have a gap, and depends on the level of the gap, it can determine the ease of the conductivity. Okay, so for the diamond, the gap is about 5.4 electron volt. So do you have an idea of this number? Again, I want to tell you, for the visible light, the energy from the red light to the blue light is from 1.8 to 3.1 electron volt. So even the UV light, even the blue light cannot let electron excite from the bonding molecular orbital to the anti-bonding molecular orbital. So this energy is high. The energy required to let diamond to become a conductor is too high. Okay? So you have few electron in this band. You have empty band here. So this is what diamond is called insulator, because it's too difficult to pump electron from the bonding molecular orbital to the anti-bonding molecular orbital. So this is what we call valence band. This is conduction band. Conduction band means the conductivity, right? Okay, valence band and conduction band. So insulator, normally the definition of insulator is this band gap is larger than 3 electron volt. Okay, and the band gap of the metal is 0, so it's a conductor. So between 0 and 3 electron volt is what we call what? Semiconductor. Okay. So this band gap, this is a definition of band gap. Please read this by yourself. And you know the definition will be different because in physics they call band gap, but for chemistry, in the chemistry they call it hormone and lumen. The highest occupied molecular orbital and the lowest unoccupied molecular orbital. They represent the same thing, but the different definition. This basically talk about molecular, basically, and this talk about the solid, a crystal. Okay. Right. So once we realize silicon, diamond, let's talk about silicon. Silicon is a semiconductor, as we know this. We already know this. So instead of 2p in diamond, silicon has 3p, 3s and 3p orbitals, right? Okay, so again you have a sp3 hybridization, and then again if you have one more of silicon gate together, and you will have the band gap like this. So what, this is carbon, this is silicon, right? And as 3p and 3s, they are the band the level, the energy level is closer than the 2s and 2p. So when you put this band gap here, have a guess, it's larger than the 5.4 or less than 5.4? Less, right? Because the s orbital 3p is much further away from the nucleus. So this energy gap will be 1.1 electron volt. So what happened to 1.1 electron volt? That means that you can use visible light to pump electron from the valence band to the conduction band, right? And what is this called? Solar cell, right? Solar cell. If you have a light from the sun and the sun hit this metal, hit these silicon crystals, and the electron jump from the valence band to the conduction band, and you give a electrical potential, and electron will move, and this is what we call solar panel, right? Solar panel. However, if you give the electricity to this material, and then the energy of electricity is high enough to pump electron from the valence band to the conduction band, and then you do nothing. And what happened? This electron will jump from the conduction band to the valence band. And how do you call this? LED, right? Light emission diode. So anyway, so the band gap of the silicon will be smaller than the band gap of the diamond. So 3sp3 electrons silicon are farther from the nucleus, in contrast of the 2sp3 carbon. So the separation between the anti-bonding and the bonding is not as great. So this is less than 5.4 electron volt. Okay, so the energy difference between the atoms orbitals and the molecular orbitals will be great for a stronger bond. So that's why we call this semiconductor, because you know, if the band gap is more than 3 electron volt, this is what we call insulator. If band gap is 0, that's what we call conductor. It's band gap between 0 and 3 electron volt, this material we call semiconductor. Okay, so as I just told you, the photon electron interaction, if I give the blue light to this silicon, this electron will be excited from the valence band to the conduction band, right? So even you use 1.1 electron volt is infrared. The energy of the photon is infrared, okay, and the heat. Anyway, you use the energy more than infrared, so you can get this. So this is what we call photon electron interaction. And this, for the application of this interaction, is solar panel, solar cell, right? And another one is photon voltaic. If we give a light to the current, this is solar cell, right? Okay, and it can have a photodetector. Remember, I don't know what are you familiar with the this kind of photodetector or not? But you know, in your camera, you always have a photodetector. Okay, so the light go into your camera, or light go to your iPhone or your mobile phone. There's a photodetector that can detect the light and grab the light and analyze the image to make a picture for you. So this is called photo detector. Okay, so if I give an external potential like electron or electricity to these materials and become light, this is what we call LED, light emitting device. Okay, we apply a voltage between this electron to this, and then the light come out. This is what we call LED. So there's semiconductor has many applications. I just give you two applications, right? Solar panel and LED. These are all made of semiconductor. Right. So now let's go back to the carbon, silicon, germanium, tin, and lead. So this is the diamond, okay, carbon, which energy band gap is 5.4 electron volt. And this 2p, 2s and 2p, right? And so n equal to 2, okay, and then now n equal to 3. The energy level is higher. Okay, this represents energy level from low to high. So this is silicon. The band gap is 1.1 electron volt. Okay, this n equal to 3. How about n equal to 4? Germanium is also a type of a semiconductor. Germanium is the energy band gap is 0.72 electron volt. Okay. Right. And then, as you know, the band gap is related, is a function of the Z, atomic number. So if atomic number increase, the band gap decrease. You might say, well, Professor, this is 4.5, 1.1, and this 0.72, which is very close to the conductor. So tin it can be regarded as a conductor, and lead is already a conductor. Right? So if atomic number increase, the band gap decrease. Right? Because this n equal to 2, 3, 4, 5, 6. So this one is insulator, semiconductor, and the conductor. Because the band gap decreases and increases. So when you regard the carbon, silicon is sp2, which is covalent bond. And germanium is also a covalent bond, but energy band gap is small. But however, for the tin, there are two forms. The one form is magnetic bond, one form is sp3 bond. The lead is totally metal bond. Okay? Why? Because many electrons, the valence electrons are so weakly held. It's too far. This is any 1, 2, 3, 4, 5, right? It's very far away from nucleus. So you have many free electrons. Okay, the band gap of conductor, semiconductor, insulator. This is metal, right? So empty. There are some overlaps. There are two types of the metals. One is filled empty band, and this is S and P overlapped, right? So band gap is 0. For semiconductor, you have small gap between valence bond and covalent bond. Covalent band, conduction band and valence band. Okay, the band gap is less than 3 electron volt. Okay, and this is the insulator. The band gap is more than 3 electron volt. Right. So this is the description of the solid state electron band structures. As you can see, if you have a single p orbital and s orbital, that means the electrons are very far, atoms are very far away to each other, so there is no interaction. But once you make it closer, atoms get closer, the band will be overlapped. So sometimes you have valence band and conduction band like this. Okay, because this is solid, this is gas. Right. And what this is I hope you still remember, the aluminum oxide is if you have a single crystal of aluminum oxide, this is transparent. diamond is also transparent, as you know. Because of what? Because the band gap is large. It's 5.4 electron volt. And if you give the visible light through this one, this visible light will pass through this diamond. So that's why you can see the letters behind this material, right? That's why, because this reflect back. So that's why when we talk about this, we talk about band gap. So there's no absorption of the light in these materials because the band gap is too huge. No absorption at all. But if you put this as a metal will absorb this energy directly and feed back to you, return back to you, so you can see the metal. But this one you cannot see because of the band gap. Okay. So that's why material properties affect many material structures, or affect many properties like electrical, thermal, optical, right? Chemical, magnetic, right? Thermal. Okay, so this is so you might have a sink, you might have a source, right? Well, professor is wonderful. So can we change the band gap? Because if we tune the band gap, we can have different property of the materials. Yes, we can. This is called band gap engineering. So for example, carbon, silicon, germanium, and tin, the band gap is 5.4 and 1.1, as you know, 0.72 and 0.08. So different band gap give you different properties of the materials. So this is 3.5. 3.5 is group 3A and group 5A, which is group 3A, which is this group. Group 5A is this group. So if you put these two elements together, it can become a semiconductor and provide you different band gap. For example, this aluminum nitride and aluminum sulfide and aluminum arsenide. Okay, nitride, phosphide, and nitride, and aluminum NEB. Okay, so have a guess. This one, the band gap will bigger than this or less than this? Bigger. Okay, and then have a guess. This one, the band gap of this will be greater than this or less than this? Small, right? Right, because n equal to 2, n equal to 3. So, and it decrease. So if you want to have a material which has a band gap of the 2.3, this is the material you need to choose. Okay? Right, so let's go to gallium nitride, gallium phosphide, gallium arsenide. So the energy here will be what? Small, right? Small, less than 6.3. You can calculate, you can do the experiment. Okay, phosphide, this one here, and arsenide. So if I give you a periodical table, I give you the comparison of this in a Kahoot. I'm sure you know how to do this, right? Finally, I got your attention. Okay, everybody start to know. When I talk about Kahoot, everybody wake up, right? Good. Okay, again, indium nitride, indium phosphide, indium arsenide. Okay, then band gap change. So this is 3.5. And do you notice? This normally you cannot see. If you see soldiers in a battle, if you see soldiers, the soldiers has when they have battle at night, they have kind of goggle, right? And they can see. But if you are enemy, you cannot see because you don't have goggle. What's that? They have this material. They can see you. You cannot see them because at night, if you cannot see anything. But with the goggle, with this material, you can see. Okay, you can see. So this is IR, night vision. You use this material. Of course, you cannot buy this easily. Otherwise, you know. Okay, right. So this is 3.5, and this is 2.6. 2.6 is this one. This is 3,5, right? And 2,6 this one. Zinc oxide, zinc sulfide. Okay. So this is CDS is visible light meter. When you have a light meter, you want to know the intensity of this light, and this is the material you use for the light meter. Okay, so interesting thing is you can tune the band gap, and you can use this band gap. You can use this material for different applications because of the different band gap. So this is what we call band gap engineering. Okay. So there's one important story to talk about band gap engineering. Is this the Nobel Prize winner in 2014 in physics? These three gentlemen got Nobel Prize because LED, I hope semiconductor is related to LED, right? LED in the past, you can only have red light and green light until the invention of the blue light. Okay, if you have this kind of three light, you can make it as a full color. That's why you can have full color display for the LED. And these three gentlemen found this, create this blue lights. Okay, when I was young, I can see only a red light and a green light. There's no blue light LED until recent. Okay, so you can make white light with this combination of these three. So you can get a lot of applications. Okay. So this is the principle of the light emission diet. I don't have time to talk about this in details. Please read this by yourself. The basic thing is you give the electricity to this device, and this electricity emit the light out, and using a semiconductor. Okay, so now LED you can not only, because of band gap engineering, not only you can make these three green light, blue light, or red light, you can also make it as an infrared. You can also use LED. You can make ultraviolet LED using this semiconductor. Okay, how wonderful, right? Right. Okay.